Hi guys, so today in this video I'm going to be going over some solubility problems from chemistry. This video will be great if you're in AP chemistry or some sort of college intro level chemistry course. I recommend that you pause the video as I go and do the questions and try them out for yourself, because sitting there and watching me doing them is great, but you're not going to learn how to actually do it without trying to do them. In this first question, it tells us what the KSP is for silver chloride, and that is 1.8 times 10 to the negative 10th. And it asks us to get what are the concentrations of Ag plus and Cl minus at equilibrium. So first, we should probably set up a chemical equation of AgCl solid is in equilibria with Ag plus Cl minus. From here, we should set up an ice table. So we go I, C, E. And because solids aren't included in equilibria, we can just put an X here. So first, for initial, what are the concentrations of Ag plus and Cl minus initially? Well, in this case, they're both 0. Okay. So next, change. Each of them is a 1-to-1 ratio with the silver chloride in the beginning. So each of these will be plus X. Plus X, plus X. So at equilibria, 0 plus X is simply X. Now that we know what the concentrations of Ag plus and Cl minus will be at equilibria, we need to set up an equilibrium constant using this and equaling it to the equilibrium constant of this. So the equilibrium constant of this equation will be KSP equals the concentration of Ag plus times the concentration of Cl minus over the reactants, but in this case, the reactant is a solid, so we don't include it in this. So we know that the concentration of this and this are both X. So I'm going to move this back up here. So we know that KSP equals the concentration of X, because that is the concentration of X is going there and X from here. So X. So we have KSP equals X times X, or otherwise known as X squared. And we can plug in our KSP from up here of 1.8 times 10 to the negative 10th. So 1.8 times 10 to the negative 10th equals X squared. And then from here it's just simple algebra, and we take the square root of each side. So our X equals the square root of 1.8 times 10 to the negative 10th. Just give me a second, I'll do this on my calculator. And on my calculator, I got X equals 1.342 times 10 to the negative 5th. So our X is that, and that will be our concentration for the silver and the chlorine ions at equilibria, and that's what the question asks for. So our answer is, I'm going to erase this. Concentration of Ag plus equals 1.342 times 10 to the negative 5th. And that also equals our concentration of Cl minus, because it is a 1-to-1 ratio. Consider mercury 1 bromide. Estimate the total Hg2 2+ concentration and the Br minus concentration if the KSP equals 5.6 times 10 to the negative 23rd. So as with the last one, we always write a chemical equation first. So mercury 1 bromide is MgBr. And that is in equilibrium with solid, I should add. Hg2 2+ plus Br minus. So this obviously isn't balanced. So what we need to do here is put a 2 in front of here and a 2 in front of here to balance it. Right? Yeah. Oh, I wrote an M there. Hg. Okay. So, as with the other one, we're going to write an ice table. So ICE. And because this is a solid, again, we just can cross it off. And nothing in the question said that there's any initial concentration of the mercury 2 plus ion or the Br ion, so these two will start with 0. And in this one, it's a 1 to 2 ratio, so where this is going to be plus x. And then this one is actually going to be plus 2x, because there's a 2 in front of the coefficient. So our equilibrium concentrations for the Hg2 plus is going to be x, and for the Br is going to be 2x. So next we need to set up our equilibrium concentration. So for this, it would be the concentration of the reactant of the products over the reactants. So it is the concentration of Hg2 plus times Br minus, and because there's 2 of them, we square it, over the reactants, but in this case, the reactants are solid, so we don't include it, equals Ksp. So now we can plug in the 2x and the x for here and here. So the concentration of Hg2 plus is just x, and the concentration for bromine, the bromine ion, is 2x. So 2x, and then squared, again because of the coefficient, equals our Ksp, which was 5.6 times 10 to the negative 23. I'm going to go back up here. So we have x, I'm going to get a different marker, x, and then 2x squared is just 4x squared. So we can combine those two terms to get 4x cubed equals 5.6 times 10 to the negative 23rd. Then we divide by 4, and this is all just simple algebra. We get x cubed equals this, which is, one sec, let me do it on my calculator. Which is 1.4 times 10 to the negative 23. And then we just take the cubed root of each side, and that'll give us our x. So again, let me do this on my calculator quick. The cubed root of 1.4 times 10 to the negative 23 is going to equal 2.410 times 10 to the negative 8th. So this is our x, and in this case, the concentration of the Hg2 plus, and the Br are different. So x equals the concentration of this, so we know the concentration of the Hg2 plus equals that number of 2.410 times 10 to the negative 8th. But in this case, our concentration of Br minus isn't the same because it's 2x. So, one sec. In this case, we just need to multiply this number by 2 because it's 2x. So the concentration of Br minus is going to equal 4.820 times 10 to the negative 8th. And that's how you do this question. Okay, so this question says the Ksp of calcium chlorate at 25 degrees Celsius is 7.1 times 10 to the negative 7th. And it asks how many grams of calcium chlorate would dissolve in 750 milliliters of water. Okay, so first off, as we're going to do with every other one, we have to write a chemical equation. So we have the calcium chlorate, solid, is in equilibria with the calcium 2 plus ion plus the chlorate ion, -1. So we have 2 of those. And this is a balanced chemical reaction. And these are both aqueous. Okay, so this is very similar to the last two we did, but it kind of adds this part of how much would dissolve in a certain amount of water. So what we're going to do is we're going to actually find the concentration of the products, and from there find how much calcium chlorate dissociated, and from there we can find how many dissolved in the water. So as with the other ones, we need to make an ice table. So since this is solid, again, we're just going to X it out. And initially, there's 0 calcium, so 0 and 0 for the chlorate as well. So the change is plus X, because there's a 1 coefficient there, plus 2X for the chlorate ion, because there's 2. And here we're going to get X and 2X, very similar to the last one we did. And then the next thing we have to do is write out the equilibrium expression, which is the concentration of Ca2 plus times the concentration of ClO3 minus 1 squared, because of the coefficient, equals our KSP of 7.1 times 10 to the -7th. From here, we plug in the X for where the calcium is, and the 2X for where the chloride ion is. And this is obviously the same as the last one we did, kind of. So we just get X times 2X squared equals that, but I'm not going to write it out. So we get X times 4X squared, or we can just simplify this to 4X cubed equals the 7.1 times 10 to the -7th. Now it's simple algebra, and we're going to divide the 4 and then take the square root of it. I'm just going to do that on my calculator real quick. You guys don't need to see the steps. So 7.1 times 10 to the -7th divided by the 4 gives us 1.775 times 10 to the -7th. And then from there, we just take the cubed root of that to get our X, which is our X equals 0.0056. Now I'm just going to erase this. So just to go over what I did, we got the X and we plugged it in for the calcium because that was the equilibrium concentration of calcium. The 2X for the chlorate, we plugged it in there. X times 2X squared is the 4X cubed equals our KSP, which was 7.1 times 10 to the -7th. I divided the 4. I took 7.1 times 10 to the -7th, divided it by 4, and took the cubed root of all of it, and I got the value over here. So I'm just going to erase this real quick. This is our concentration of here, and our concentration of this. 2 times this will be our concentration from here. So we know that X concentration is this, and the calcium chlorate and the calcium have a 1-to-1 ratio. So from this we can deduce that because the change was 0.0056 molar, that this lost 0.0056 molar as well. So the calcium chlorate lost this number, the 0.0056. So from here, we we have the molarity value, but that's not what we want. We want to know how many grams it lost. So molarity is moles per liter. So next thing we need to do is convert this to grams. So how many grams are in 1 mole of this? Well, first, to do that, we need to add up the molar mass of that compound. So calcium, having a molar mass of 40, plus chlorine, which has a molar mass of 35.45, and there's 2 of them, so plus 35.45, and then there's going to be 6 oxygen because the O3 times the 2, so plus 6 times 16, which is the molar mass of oxygen, and I'll do that on my calculator real quick, times 6. So the molar mass of calcium chlorate is 206.9 grams. So now we can use this value to help convert our moles per liter to grams per liter. So in 1 mole, we're going to do some dimensional analysis. In 1 mole, there is 200. Let me get my other pen. There is 206.9 grams, which is the molar mass of the calcium chloride once again. So the mole and the mole cross out when we're multiplying them. So we find that 206.9 grams per liter. So this lost 206.9 grams per liter. But our molarity was only 0.0056, so we do this times 0.0056, which gives us 0.0056, 1.158. 1.158. God, my markers are going bad on me. I'm sorry. 1.158. So what this number is grams per liter, is how many grams the calcium chlorate lost per every liter it is dissolved in of water. Okay, I'm just going to move this number over here. So we have 1.158 grams per liter. But there's only 0.750 milliliters of water is getting dissolved in. So we can just take this, and we need to do dimensional analysis again. And for one liter, there's 1,000. No, we wouldn't do it that way. We can just simply multiply it by 750 over 1,000, because this is how many milliliters there are in a liter. And we find, by multiplying 1.158 times 3/4, which is the reduced fraction of that, that the calcium chlorate lost 0.868 grams to the solution, which is what we were looking for, is how many grams of the calcium chloride would dissolve in the 750 milliliters of water. So that's our final answer. So in this last question, it says calculate the solubility of AgCl in water and 0.1 molar NaCl with the KSP of the AgCl being 1.8 times 10 to the negative 10th. So this is really similar to the first one we did, but the only difference is there's already something that's in the solution. It's not just water. So just as every single one, first we need to write the chemical equation of the dissolution of AgCl. So first we have AgCl solid going to Ag aqueous plus Cl minus. And like the other ones again, we're going to make an ice table because to find the solubility, we need to find how many moles per liter of AgCl are lost to the solution. So we make an ice table, ICE. And again, like in all the other ones, the AgCl is a solid, so we can just cross this out. So in all the other ones, we would just write 0 and 0 for here. But in this, it's not the case. There is 0.1 molar NaCl in the solution. So that means that there's going to be 0.1 moles of, there's going to be 0.1 molar Na plus, and also 0.1 molar Cl minus, because NaCl dissolves completely in water. So the Na isn't part of this equation, so we can ignore the Na plus ion, the 0.1 molar of that. But there's already going to be 0.1 molar of the chlorine ion in the solution. So initially there is 0.1 molar. And for the Ag, there's no Ag in here, so we can just put this as 0. And this is the same as the other one, so the change is plus X. So our equilibrium value for the Ag plus will be X. And for the chlorine this time, instead of just being X, it'll be 0.1 plus X. Okay, so as in all the other ones, we can use these and the KSP value to find what our X's are. So our equilibrium expression is the concentration of Ag plus times the concentration of Cl minus over the reactant, which is a solid, so we leave it, equals the KSP, which is 1.8 times 10 to the negative 10th. And from here we can plug these values into their spots. So X times 0.1 plus X equals 1.8 times 10 to the negative 10th. So you could just do this and distribute the X and solve for X, but realistically, not that much is going to be dissolving into the solution because we know the KSP is so low. So this X right here is actually insignificant because if, let's say, the X is, since this is so low, if it's like 0.0000 some number, 0.1 plus that really tiny number isn't really going to make that big of a difference in the value of this. So we can just kind of negate the X here and just make it X times 0.1 equals this, times 10 to the negative 10th. So again, the reason why we did that is since the KSP of AgCl is so low, our X value we can kind of predict is going to be tiny because it's 1.8 times 10 to the negative 10th. So this X that's getting added, since it's going to be such a small number, it really doesn't matter. So we can just kind of pretend like it doesn't exist and just make it this. So from here, it's just algebra, and we divide the 0.1, and we find that our X is 1.8 times 10 to the negative 10th divided by 0.1 is going to be 1.8 times 10 to the negative 9th equals 1.8 times 10 to the negative 9th molar. So that is what our X is. And because the AgCl and the Ag is a 1-to-1 ratio, we know that the AgCl will lose as much as the Ag plus gained. So the solubility of the AgCl in this solution in 0.1 molar NaCl simply just equals this, the 1 0.8 times 10 to the negative ninth. Again, the reason for this is 1.8 times 10 to the negative ninth molar is how much the Ag gained, the Ag ion gained. So that'll be the same as what the silver chloride lost, and that is the solubility of Ag chloride in NaCl. So thank you guys for watching this video. I know it can all be kind of tricky at first, but the more you practice, the better it'll get. Personally for me, someone who eventually did really well in chemistry, I struggled when I first started with hard topics like this, but it'll all come together once you practice more and more. Thank you for watching this video, and I hope you learned something.